Hello everyone, welcome to my class. Today we start chapter 7. Chapter 7 is about techniques of integration. Let me start the class right away. First, a quick preview. In Calculus 2, the functions that we integrate are of elementary functions. There are several techniques of integrations, and note that not all continuous functions are integrable. For example, e to the x square is not integrable. Let me remind you, in Calculus 1 we learned two techniques of integrations. First technique was using a table of indefinite integrals, and the second technique was using a u substitution, what we call u sub. Now we will study some other general technique of integrations. So in chapter 7 we study integration by parts technique, trigonometric substitution technique, partial fractions technique, numerical technique, which is also called approximate integrations. So it happens sometimes we cannot find the exact value of integrations, then we use numerical technique to approximate the value. And we end this chapter by exploring the improper integrals. So now let me start the integration by parts technique. Let me scroll down. Integration by parts, or in short form we write IBP. IBP is a technique for integrating a product of functions. So before that, let me start with recalling a u substitution. The u substitution is a corresponding integration rule to the chain rule for differentiation. The u sub is a technique of integrating a product of functions and its a derivative. That is, we use u substitution if you integrate an integral of type f of gx times g prime x. For example, evaluate the integral x times radical x squared plus 1, or evaluate integral sine x times cosine x. So here in the first example we can substitute u equals to x squared plus 1, then its derivative turns out to be du equals to 2x dx, and I have x dx, the remaining term in the integral I can easily replace in u term, means in u variables, and keep in mind that we always manipulate the constant. Great. Similarly, in the second example, you can either substitute u equals to sine x, then its derivative turns out to be cosine x dx equals to du. So the cosine x dx is here. You can easily replace by du. Or we can substitute u equals to cosine x, then its derivative turns out to be du equals to negative sine x dx. And sine x dx is here. We can easily replaced by negative du. Great. But the question arises here, what happens if we have an integral with integrand function, a product of two functions, but one function is not a derivative of the other functions? For example, the questions here, how to evaluate integrals of type integral x times sine x, or x times e to the x, or integral of x times natural log of x, or even integral of sine x times natural log of x, or the integral of type e to the x times ln of x, because none of the function is a derivative of the other one on that particular integral. Then the answer is we need to use integration by parts formula. Great. So then let's start integration by parts formula. Let me scroll down. That's better. So the IBP is a corresponding integrations rule to the product of differentiation. What's the product of differentiation? Which I give you here. The product rule of derivative is d over dx of f of g equals to g f prime plus f g prime. Then let's rearrange the term. Let's take this second term to the left side. Then g f prime equals to d over dx f of g minus f of g prime. Let's integrate both sides. On the left side, the integration of gx f prime x dx. So keep in mind that I took x as my independent variable. And on the right side, on the first term here, the integration and d over dx cancel out. So this only gives me f of x, g of x. And then minus as it is, integral of fx, g prime x dx. This formula, or this expression, is called the integration by parts formula. More precisely, let's assume u equals to gx and v equals to f of x. Then this formula reduced to integral u dv equals to uv minus integral v du. So it's just easy to get that one from here. So this is g is u, f prime x is dv, and fx dx is ub, fx is v, g prime is du. So now onwards, by IBP formula, we recognize the integral of this form. Integral of u dv equals to uv minus integral of v du. So on the left side, I have a product of two functions here. Okay, u is one function, dv is another function. Great. So now let me give you some side note. So first side note, in IBP formula, it's tricky to pick u value for one function and dv value for the other function. So if we are able to pick u value, then the dv value will be everything in the given integrals. And there are four values on our IBP formula. One is u, one is dv, one is v, one is du. Once we pick u and dv from the given integral, then we can find du by taking the derivative of u. We can find v by taking integration of dv. So that means our choices functions, u should be differentiable and dv should be integrable. And with the correct choices of u and dv results the new integrations, which is integral of v du, that turns out to be easily integrable comparing to the given integral. I hope this makes sense to you all. And side note number 2, sometimes light principle is helpful to choose u value and dv value. So the light stands for, L stands for logarithmic functions, I stands for inverse trigonometric functions, A stands for algebraic functions, T stands for trigonometric functions, and E stands for exponential functions. Great. So if our integrand function is a product of any one or any two of these functions, then always we pick the first one for u. Okay. For example, if I have logarithm function and algebraic functions, then we pick u equals to logarithmic functions. Great. Side note number 3, in some cases we need to repeat the IBP formula twice or even more than twice. Great. So let me scroll down. Right. So let me explain the IBP technique in tabular method. So there are two columns. One is u column, u should be differentiable. Another column is dv column, dv should be integrable. Under the u, take the derivatives. So derivative of u is du. Under dv, take integral. So integration of dv is simply v. Then multiply the second row by negative sign, so I multiply by negative here. Then in the next step, multiply diagonally, then u times v, multiply straight across, so negative du times v. Keep in mind that the straight across multiplication is an integral term, so we have integral of negative v times du, and then the next step, add these two results, that is our IBP formula which I gave here. So uv minus integral v du, this minus is this minus. Great. And sometimes we need to repeat the IBP formula twice or even thrice or even more than thrice, then we continue this table. So the idea is I gave you here. Let me read it through. Under u column, repeatedly find derivatives. Find derivatives. Under dv column, repeatedly find integrations. So find integration under dv column. Add a negative sign to every second row. That means even row. So here is the second row, then fourth row, then sixth row, then eighth row, and so on. Next, multiply diagonally continuously. Multiply diagonally continuously. And lastly, multiply straight across and add them all. Lastly, multiply straight across. Multiply straight across. And keep in mind that straight across multiplication is an integral term. So stop when straight across multiplication gives an easier integral. Great. Now, now let's use IBP and evaluate some integrals. So first example, evaluate the integral of type x times cosine 3x. So here our integrand function is a product of algebraic functions and trigonometric functions. So let's begin the solution. Solution, make a table, two columns, u column and dv column. Pick u equals to x, dv equals to cosine 3x. Under the u column, take the derivative, so x derivative is 1. Under dv column, take the integration, so integration of cosine 3x is sine 3x over 3. Then IBP formula says multiply diagonally, multiply by minus to the second row, and multiply straight across, which will be our integral terms. Okay, so which is here. So x times sine 3x over 3, x times sine 3x over 3, minus this minus sign, then the integral 1 times sine 3x over 3 dx. Then we can easily integrate this new integral. So copy the first term as it is, then the minus 1/3 outside, and the integral of sine 3x produce another minus. So minus cosine 3x over 3, then this minus becomes plus, and 1/3 and 1/3 and 1/3 is 1/9 cosine 3x plus c is a constant of integrations. So here's I have one more row here on my table. So here's, if I keep on continuing taking derivative under u column, then derivative 1 becomes 0. Keep on taking integral under dv column, so the integral of 1/3 sine 3x becomes negative 1/9 cosine 3x. So that means this term's integrations turned out to be this term, right? So minus 1 times minus 1/9 is plus 1/9, and the cosine 3x. Great. So that means I can keep on multiplying the diagonally. So x times sine 3x over 3, then plus 1/9 cosine 3x, and then the last term will be the straight across multiplications, which is an integral term, but here it turns out to be 0, then plus c. Great. So I hope this explanation makes sense to you all. Now let me continue. Let me scroll down. Great. So let's do example 2. Evaluate the integral of type x squared times ln x. So here our integrand function is a product of algebraic functions times the logarithmic functions. So let's begin the solution. So make a table. First column is u column, second column is dv column. Keep in mind that u column should be differentiable, dv column should be integrable. So I pick u equals to ln x, then dv equals to x squared dx. You might be wondering why I pick u equals to ln x. If I pick dv equals to ln x, then in the next step I need to take integration of ln x. Then either we don't know the formula of integral of ln x at this time, or the integrals of ln x is slightly harder than derivative of ln x. The derivative of ln x is simply 1 over x, but integral of ln x is x ln x minus x. We have to use IBP to find the integration of ln x. So that's one reason I pick u equals to ln x. Another reason is, if you remember our light principle that I talked earlier, where L stands for logarithm functions, so always logarithm function comes first on our light principle, means our u choice is log functions. Great. Now let's continue. So in the next step, means in the next row on our table, under u column, take the derivative of ln x, which is simply 1 over x. Under dv column, take the integral of x squared, which is simply x cubed over 3. Multiply the second row by negative. Then apply the IBP formula. So the given integral is equals to, multiply diagonally, so x cubed over 3 times ln x, and then this minus as it is, minus, and the integral of, multiply straight across, so 1 over x times x cubed over 3 dx. Great. The first term in the next step, first term copy as it is. We can cancel the x and x cubed, so we have x squared left, and we can pull the 1/3 outside, so minus 1/3 outside the integral, and the integral of x squared becomes x cubed over 3 plus constant of integration c. Great. So let me scroll down. Then in the next step, let's simplify here. So the first term as it is, x cubed over 3 times ln x, minus 1/3 times 1/3 is 1/9 x cubed plus c. Great. Now let's continue. Great. Let's do example 3. Evaluate the integral of e to the x times sine x. So here, this times the integrand function is a product of exponential times trigonometric functions. Great. So let's begin the solution. Make a table. Pick u equals to e to the x and dv equals to sine x dx. Under the u column, take the derivative of ex itself, ex. Take the integral under dv column, integral of sine x, which is negative cosine x. If you focus on the second row here, the straight across multiplication gives you an integral of e to the x times cosine x, which it seems to me not easier than the given integral, because given integral is also integral of exponential times trig functions. So let's repeat one more times the IBP. So that means take one more times derivative of e to the x under u column, which gives me the third row, e to the x. Take integral under dv column, integral of cosine x, which gives us sine x. And now let's focus on this third row. Straight across multiplication gives us integral of e to the x sine x. Wow. We started taking integral of e to the x times sine x. now we ended up with an integral of e to the x times sine x. So that means we sort of making a loop here, right? So that means we use IBP twice, formula here. Then the given integrals, I assume I equals to integral e to the x sine x dx. This equals to multiply diagonally, so ex times negative cosine x, so then minus ex times cosine x, and multiply diagonally one more times, and the second row and then the third row here, so e to the x times negative sine x, there is a minus sign, so positive ex sine x, and then lastly multiply straight across, that's an integral term, so integral minus sine x ex or ex sine x dx, and plus c at the constant integrations. Great. So on my left side I have an integration of ex sine x, and my right side the new integral also turns out to be integral of ex sine x. Now I can add these two integrals. Then in the next step, add those two integrals. Then I have 2 times I equals to, I factor the e to the x outside, then e to the x out, so left negative cosine x plus sine x plus c. Divide both sides by 2, then I equals to 1/2 e to the x negative cosine x plus sine x plus c. Let me scroll down. So I is the integral of e to the x sine x dx. So its value turns out to be 1/2 ex, and with no reason I switched the position here, so I first wrote positive term and then the negative term, and then plus c as it is. Great. So let's do example 4. Evaluate an integral of x squared times e to the 3x. Here I have an integrand function is a product of algebraic function times exponential functions. Now begin the solution. Make a table. So pick u equals to x squared, then dv equals to e to the 3x dx. Under u column, take the derivative. Under dv column, take the integrations. So on my second row, derivative of x squared under u column becomes 2x. Then take the derivative of 2x, becomes 2. Take the derivative of 2, becomes 0. Under dv column, take the integrations. Integration of e to the 3x becomes 1/3 e to the 3x. Take the integral of 1/3 e to the 3x becomes 1/9 e to the 3x. Take the integral of 1/9 e to the 3x becomes 1/27 times e to the 3x. So if you saw the pattern here, on each derivative under u column, it kills the power of this algebraic function here. X squared becomes x becomes then 1, and then 1 becomes 0 there. Great. So then let's apply the IBP formula. Then by IBP formula, multiply diagonally, multiply by -2 each even rows, so that means second rows and the fourth rows, and multiply diagonally, and at the very end multiply straight across and add all of these results. So the first term on my right side will be x squared times 1/3 times e to the 3x. Then the second term will be this negative, so negative 2x over 9 e to the 3x. And the third term will be 2 over 27 e to the 3x. And then my last term will be plus, I need to multiply straight across, but the 0 times the term is 0, so I don't need to write the 0. Then I add plus c. C is a constant of integrations. Great. So now let's move on. Now a final remark, sometimes we use combination of a different integration technique. So far we studied use of an IBP technique, so let me combine these two techniques. In example 5, evaluate, I denote the integral by I, so I equals to integration of x cubed times sine x square dx. Note that we cannot integrate of sine x square. So first let's use u substitutions. So put u theta equals to x square. So I put theta variable here. I reserve the u for integration by parts formula. After we put theta equals to x square, take the derivative. So d theta equals to derivative of x square becomes 2x dx. Divide by 2 both sides, then x dx equals to d theta over 2. Then I use one small trick here. I break down x cubed as x times x square so that I can plug theta equals to x square, and then this x goes to the dx, which is here d theta over 2. Great. So then let's rewrite the given integral in terms of new variable theta. So then I equals to integration x square is theta, sine x square is simply sine theta, then x times dx is d theta over 2. Great. In the next step, I can pull the constant 1/2 out, then integral of theta times sine theta d theta. Now this integral is a good candidate for IBP, right? The integrand function is a product of algebraic functions times trigonometric functions. Great. Let me scroll down. So then let's apply IBP, make our table. So first column u column, second column dv column, pick u equals to theta, then dv equals to sine theta d theta. That's better. Then under the u column, take the derivative of theta. Derivative of theta with respect to theta is 1, and take the derivative 1, which is 0. Under dv column, take the integrations. Integration of sine theta is negative cosine theta, and integration of negative cosine theta is negative sine theta. And under the u column, our derivative ends in 0, so we stop here. Great. Then this given integral equals to 1/2 constant as it is. Then by the IBP formula, let's multiply diagonally and straight across. So here this is theta times minus cosine theta, so minus theta cosine theta. And then this minus times this minus is plus, so 1 times sine theta is sine theta, and then the plus multiply straight across, so 0 times minus sine theta is 0, so I don't need to write the 0, then write plus c. C is a constant of integrations. Great. Now finally reverse the substitutions. Our substitution was theta equals to x square, so the last line here 1/2 as it is, minus theta is x square, so minus x square times cosine x square plus sine x square plus c. That's our final answer. Great. Now let me talk about reduction formula. What it does, the reduction formula reduces the degree of power every times. So for example, recall we know the integral of sine x is negative cosine x. But what if integration of sine square x? This does not equals to cosine square x. But we need to use a reduction formula. The reduction formula reduces the power 2 to 1, then we can apply this formula. Similarly, what's an integral of sine cube x? This is not equals to cosine cube x. Instead, we need to apply reduction formula, and reduce the power from 3 to 2 or 2 to 1 and apply this non-integrals. Great. So let me give you I'll give you this reduction formula for general n. So the formula is integration of sine to the power n is equals to -1 over n times sine to the power n minus 1 x times cosine x plus n minus 1 over n times the integral of sine to the power n minus 2x dx. So that means we started taking the integral of sine x of power n, then it reduced from power n to the power n minus 2. So that means in the next step it reduced the power to n minus 4, then n minus 6, then blah 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 to power 3, power 2, and to power 1. That means sine x. Then we can apply this formula. So that's the idea. Great. So for example, integrate sine square x dx. So here n equals to 2. So then using this formula, minus n is 2, so 1/2, n is 2, so sine to the power 2 minus 1 is sine power 1, that means sine x. Then next is cosine x plus 1/2 integrations sine to the power 2 minus 2 is 0, so sine power 0 is 1, so simply dx. And in the next step I use a trigonometric identity. We know 2 sine x cosine x is sine 2x, so I multiply and divide by 2. So then in my denominator I have 4, so -1/4, then 2 sine x cosine x becomes sine 2x, then plus 1/2 as it is, integration of dx is simply x, plus constant of integration c. Great. Similarly, example 7, integration of sine qx dx. Now put n equals to 3. So by this reduction formula, our answer is -1/3 sine square x cosine x plus n is 3, so 3 minus 1 is 2, 2 over 3, so 2/3 integration sine x dx. N is 3, so 3 minus 2 is 1, so simply sine x. Then the next step, -1/3 sine square x cosine x plus 2/3, and integral of sine x gives me minus cosine x, that's where this minus comes from. And then, not dx, instead dx, let me hide it, plus c. So the final answer is, for example 7, -1/3 sine square x times cosine x minus 2/3 cosine x plus c. Great. Let me move on. So here I gave you the general idea to prove the reduction formula, but I'm not going to prove here, and I will not ask you to prove the reduction formula in the exam also. So the idea is the integral of sine to the power nx dx, we break down sine to the power n as sine to the power n minus 1 times sine to the power 1x. Then we pick u equals to sine to the power n minus 1x and dv equals to sine x dx. Apply this IBP formula technique, and then it gives us the formula that we used before. Let me scroll down. Similarly, the integral of cosine n power x becomes 1 over n cosine n minus 1 power x times sine x plus n minus 1 over n times integral of cosine n minus 2 power. Similarly, the reduction formula for tan to the power nx is 1 over n minus 1 times tan to the power n minus 1 minus integral of tan to the power n minus 2. Great. Now let me do the last example for this section. Example 8. Let's evaluate integral of ln x, and b, integral of tan inverse x. Great. Begin the solutions. We don't have much choices for u and dv in these examples. Ln x. So here's the idea is we don't know the integral of ln x. So to apply the IBP formula, then I need to assume u equals to ln x. So then dx will be my dv, because dv is integrable, right? And similarly in the case b also, I need to assume u equals to tan inverse x, then dx will be my dv. That's the idea. Good. So it's a quick solution here. So make a table, u and dv, u, pick u equals to ln x, then dv equals to dx. Take the derivative of ln x, which is 1 over x. Take the integration of dx, which is x. And multiply the second row by negative. Then in the next step here, apply the IBP. So integral ln x dx equals to multiply diagonally. So x times ln x. Then minus multiply straight across, that's the integral term. So the integral of x times 1 over x, cancel xx, just simply 1 times dx. Then the last step, copy the first term, x times ln x, and then integral of 1 is simply x, then plus c. C is constant integration. So now we know the integral of ln x is x ln x minus x plus c. Awesome. Similarly, b, so here tan inverse x. So pick u equals to tan inverse x, then dv equals to dx. Take the derivative of tan inverse x, which is 1 over 1 plus x squared. Take the integration of dx, which is x. Multiply the second row by negative, so I put my minus sign there. And using IBP, given integral equals to, multiply diagonally, x times tan inverse x, and add, multiply the straight across, that's the integral term, but this minus gives me this minus here, integral of x over 1 plus x squared dx. The new integral is a good candidate of u substitution, so put u equals to 1 plus x squared, then its derivative turns out to be 2x dx equals to du. Then divide both sides by 2, so then x dx equals du over 2. Then rewrite this integral in terms of u, then this becomes minus 1/2 du over u. And we know the integral of 1 over u is simply log, means natural log of u. And resubstitute our u variables, u equals to 1 plus x squared, which turns out to be this one. So our final answer is x times tan inverse x minus 1/2 natural log of 1 plus x squared plus c. C is a constant of integrations. Great. So we finish the integrations by parts technique. In the next class, we'll study trigonometric integrals. So thank you.